Hello. Welcome to the online lesson on the Geography of Turkey 1, Physical Geography of Turkey course. In today's session, we will delve into the pedologic features of Turkey. Soil is a complex and dynamic natural resource that forms the uppermost layer of the Earth's crust. It is a mixture of mineral particles, organic matter, water, air, and living organisms. Soils play a crucial role in supporting plant life, serving as a medium for plant growth and providing essential nutrients. Here are key components and functions of soil. Components of soil. 1. Mineral particles. These include sand, silt, and clay, and their proportions determine the soil texture. The combination of these particles influences water retention, drainage, and nutrient availability. 2. Organic matter. Decomposed plant and animal material contribute to soil organic matter. It enhances soil structure, water retention, and nutrient content. 3. Water. Soil serves as a reservoir for water, crucial for plant hydration and various biological processes. 4. Air. Spaces between soil particles allow for air movement, providing oxygen for plant roots and soil organisms. 5. Living organisms. Soil is home to a diverse community of microorganisms, including bacteria, fungi, insects, and earthworms. These organisms contribute to nutrient cycling and organic matter decomposition. Functions of soil. 1. Plant growth medium. Soil provides physical support and anchorage for plants. Root systems extract water and nutrients from the soil for plant growth. 2. Nutrient storage and cycling. Soils store essential nutrients like nitrogen, phosphorus, and potassium, releasing them to plants as needed. Microorganisms play a key role in nutrient cycling. 3. Water regulation. Soil regulates water movement, preventing runoff and erosion. Proper water retention and drainage are critical for plant health. 4. Biological habitat. Soil hosts a diverse range of organisms, forming a complex ecosystem. These organisms contribute to nutrient cycling, pest control, and soil structure. 5. Filtration and purification. Soil acts as a natural filter, removing impurities and contaminants from water as it percolates through the soil profile. 6. Carbon storage. Soil stores a significant amount of carbon, helping mitigate climate change by sequestering carbon dioxide from the atmosphere. 7. Construction material. Certain types of soil, like clay and loam, are used in construction activities for making bricks, ceramics, and other building materials. Soils vary widely in composition, texture, and properties, leading to diverse soil types around the world. Understanding soil is essential for sustainable agriculture, environmental conservation, and land management. Weathering is the process by which rocks and minerals on the Earth's surface break down and disintegrate into smaller particles over time. It is a fundamental geological process that occurs due to various mechanical, chemical, and biological actions. Weathering plays a crucial role in shaping the Earth's landscape and contributing to the formation of soils. There are two primary types of weathering. 1. Mechanical weathering, physical weathering. This type of weathering involves the physical breakdown of rocks into smaller fragments without altering their chemical composition. Several mechanisms contribute to mechanical weathering, including frost wedging. The expansion of water as it freezes and rock fractures can cause the rock to break apart. Temperature changes. Alternating cycles of heating and cooling can lead to the expansion and contraction of minerals, resulting in cracking. Biological activity. Plant roots, burrowing animals, and other living organisms can exert pressure on rocks, causing them to break. 2. Chemical weathering. Chemical weathering involves the alteration of the mineral composition of rocks through chemical reactions. Some common processes of chemical weathering include hydration. The addition of water to minerals causes them to absorb water molecules and undergo changes in structure. Oxidation. The reaction of minerals with oxygen, often leading to the formation of rust on iron-bearing minerals. Carbonation. The dissolution of minerals, particularly carbonate minerals like limestone, in acidic water. Hydrolysis. The reaction of minerals with water, resulting in the breakdown of minerals into new substances. Weathering is often a combination of both mechanical and chemical processes acting on rocks simultaneously. The products of weathering, known as sediments, contribute to the formation of soils and are transported by erosion and deposition to different locations. Weathering is a continuous and ongoing process that occurs in response to environmental conditions, and it plays a crucial role in the Earth's geological cycle. One of the most important conditions for soil formation is the process of disintegration of the main rock, which is a solid whole. The scientific term for the disintegration process is weathering. Weathering is the process by which rocks and minerals on the Earth's surface break down and disintegrate into smaller particles over time. It is a fundamental geological process that occurs due to various mechanical, chemical, and biological actions. Weathering plays a crucial role in shaping the Earth's landscape and contributing to the formation of soils. Soil formation, also known as pedogenesis, involves a series of complex processes that transform unconsolidated rock material into soil. The stages of soil formation can be broadly categorized into the following. 1. Weathering. Physical weathering, mechanical breakdown of rocks into smaller particles due to factors such as frost action, temperature changes, and the activities of plants and animals. Chemical weathering, alteration of mineral composition through chemical processes like hydration, oxidation, carbonation, and hydrolysis. 2. Addition of organic material. Dead plant and animal material, along with microorganisms, contribute to the organic content of the soil. This stage involves the accumulation of organic matter on the surface. 3. Leaching. Water moving through the soil profile carries away dissolved minerals, a process known as leaching. This can result in the removal of certain elements from the soil. 4. Eluviation. The deposition of leached materials in a lower soil horizon. This can lead to the development of distinct layers or horizons in the soil profile. 5. Horizon development. The formation of soil horizons or layers with distinct characteristics. Common horizons include the O horizon, organic matter, A horizon, topsoil, B horizon, subsoil, and C horizon, weathered parent material. 6. Soil profile maturation. Over time, the soil profile becomes more mature and develops distinct horizons. The interactions between climate, organisms, topography, and parent material contribute to the unique properties of different soil types. 7. Soil differentiation. The process where soils in a region develop distinct properties based on environmental factors. Different climates, vegetation types, and parent materials can lead to the formation of diverse soil types. 8. Soil classification. Soils are classified into various orders, suborders, and groups based on their properties. This classification system helps scientists and farmers understand the characteristics and potential uses of different soils. These stages are interconnected and can occur concurrently or sequentially depending on environmental conditions. Soil formation is a dynamic and ongoing process influenced by factors such as climate, topography, organisms, and time. Weathering is the process by which rocks are broken down into smaller particles through various physical, chemical, and biological mechanisms. Several factors influence the rate and type of weathering. 1. Climate. Temperature. Higher temperatures generally accelerate chemical reactions and increase the rate of weathering. Precipitation. Water facilitates both physical and chemical weathering. Regions with high rainfall often experience more rapid weathering. 2. Rock type. Mineral composition. Some minerals are more resistant to weathering than others. For example, quartz is relatively resistant, while minerals like feldspar are more susceptible. 3. Vegetation. Plant roots can physically break rocks apart. Additionally, the organic acids released by roots during processes like root respiration can contribute to chemical weathering. 4. Topography. The slope of the land can affect the drainage of water, influencing the amount of time rocks are exposed to weathering agents. 5. Biological activity. Activities of burrowing animals, such as earthworms, contribute to the physical breakdown of rocks. 6. Time. Weathering is a gradual process, and the longer rocks are exposed to weathering agents, the more they break down. 7. Human activities. Anthropogenic factors, such as pollution and the extraction of resources, can accelerate weathering processes. 8. Water and ice. Freeze-thaw cycles, common in cold climates, can physically break rocks as water seeps into cracks, freezes, and expands. 9. Wind. Wind-blown particles can physically abrade rocks, a process known as abrasion. 10. Chemical agents. Acids, rainwater, especially in polluted areas, can become acidic and enhance chemical weathering. Oxygen, oxidation reactions, where minerals react with oxygen, contribute to weathering. Understanding these factors helps geologists and scientists predict the weathering rates in different environments. The combination of these factors determines the specific characteristics of weathering in a particular location. Physical or mechanical weathering involves the breakdown of rocks into smaller fragments without changing their chemical composition. This process is primarily driven by physical forces. Various mechanisms contribute to physical weathering. 1. Frost action, frost wedging. Water seeps into cracks in rocks. When the water freezes, it expands, exerting pressure on the rock. Repeated freezing and thawing can gradually widen cracks and break the rock into smaller pieces. 2. Temperature changes. Daily temperature fluctuations can cause rocks to expand and contract. This expansion and contraction can lead to the development of cracks and fractures, especially in rocks with different minerals that expand and contract at different rates. 3. Exfoliation. This process involves the peeling away of outer layers of rocks. It occurs due to the release of pressure on rocks as overlying material erodes away. The reduced pressure causes the outer layers to flake or peel. 4. Biological activity. Plant roots can grow into cracks in rocks, exerting pressure as they expand. Burrowing animals and insects can contribute to the physical breakdown of rocks by creating passageways and fissures. 5. Salt crystal growth. Water containing dissolved salts infiltrates rocks. When the water evaporates, salt crystals are left behind, exerting pressure on the rock surfaces. This process can lead to the mechanical breakdown of rocks. 6. Abrasion. Abrasion involves the physical wearing down of rocks by the impact of particles carried by wind, water, or ice. Wind-blown sand, river pebbles, and glacial debris can abrade rock surfaces over time. Physical weathering is particularly effective in environments with temperature variations, freezing and thawing cycles, and the presence of plants and animals. It contributes to the initial stages of soil formation by breaking rocks into smaller particles. Climates with more pronounced temperature fluctuations and the presence of frost action are conducive to increased physical weathering. The following climatic conditions and environments often experience more significant physical weathering. 1. Cold and freezing climates. Regions with cold climates, especially those with freezing temperatures, are prone to frost action. Alternating cycles of freezing and thawing contribute to the breakdown of rocks through frost wedging. 2. Mountainous environments. Mountainous regions often experience rapid temperature changes, especially at high altitudes. The steep slopes and rugged terrain in mountains increase the likelihood of physical weathering, including rockfall and abrasion. 3. Glacial environments. Glaciers, with their immense weight and movement, can physically break down rocks. Glacial abrasion, where rocks are embedded in the glacier's base, contributes to the mechanical weathering of bedrock. 4. Arctic and subarctic regions. Cold climates in Arctic and subarctic regions lead to the formation of permafrost. Permafrost can cause ground contraction and the development of ice wedges, promoting frost-related physical weathering. 5. Alpine regions. High-altitude alpine environments experience temperature fluctuations and freeze-thaw cycles. The combination of freezing temperatures and the presence of glaciers can enhance physical weathering processes. 6. Desert environments. Despite being characterized by arid conditions, some deserts experience temperature extremes. Diurnal temperature variations in deserts, where daytime temperatures are high and nighttime temperatures drop significantly, contribute to physical weathering. It's important to note that while physical weathering is influenced by climate, other factors such as the type of rock, geological structures, and the presence of vegetation also play significant roles in the weathering processes observed in different regions. The term jumbo rocks refers to a prominent rock formation and campground within Joshua Tree National Park in southeastern California, USA. Joshua Tree National Park is renowned for its unique desert landscapes, geological formations, and the iconic Joshua trees. Location: Jumbo Rocks is situated in the northern part of Joshua Tree National Park, known for its extensive and fascinating rock formations. Rock features: the area is characterized by large, rounded granite boulders and rock piles, creating a stunning and surreal landscape. A fog bow is a meteorological phenomenon similar to a rainbow but appearing in foggy conditions. It is created by the diffraction, or bending, of light as it interacts with water droplets in the air. Here's information about a fog bow over the tundra in Siberia. Location: the tundra in Siberia, Russia. Phenomenon: a fog bow, which is a colorless or pale bow similar to a rainbow, but with the colors often indistinct or washed out. Cause: fog bows, like rainbows, are formed by the reflection, and dispersion of light in water droplets. In the case of fog bows, the water droplets are much smaller than raindrops, leading to a diffused and less colorful appearance. Conditions: fog bows typically occur in areas of fog or mist where sunlight interacts with the tiny water droplets suspended in the air. The tundra's unique environmental conditions, combined with fog or mist, could create an ideal setting for the formation of a fog bow. Appearance: fog bows are often characterized by their pale or white coloration, and the visibility of the bow depends on the size of the water droplets and the angle of the sunlight. Observing a fog bow can be a captivating experience, especially in regions with atmospheric conditions conducive to the formation of these ethereal and subtle optical phenomena. Salar de Uyuni is the world's largest salt flat, located in the Altiplano region of southwest Bolivia, in the Potosi district. Here's some information about Salar de Uyuni. Size and formation: Salar de Uyuni covers an area of over 10,000 square kilometers, 3,900 square miles, making it the largest salt flat globally. It was formed as a result of transformations between several prehistoric lakes. Salt thickness: the salt crust covering the flat is exceptionally flat, with an average thickness of about 7 meters, 23 feet. Beneath the salt crust is a pool of brine. Salt extraction: the salt flat contains a significant portion of the world's known lithium reserves, and it is a major source of salt extraction for Bolivia. Unique landscape: the landscape of Salar de Uyuni is otherworldly, especially during the rainy season when a thin layer of water turns the flat into the world's largest natural mirror. This phenomenon creates breathtaking reflections of the sky and clouds. Hexagonal patterns: the salt crust often forms hexagonal patterns, creating a mesmerizing visual effect. Isla Incahuasi, located in the center of the salt flat, Isla Incahuasi is an island covered in giant cacti and is a popular stop for tourists. Tourist attraction: Salar de Uyuni is a major tourist attraction, drawing visitors from around the world who come to witness its unique landscapes and experience the surreal reflections during the rainy season. Astronomical observatory: the flat's vast, flat surface makes it an ideal location for astronomical observations, and there are proposals for building an astronomical observatory on the salt pan. Visiting Salar de Uyuni is a unique and unforgettable experience, offering a glimpse into the extraordinary landscape shaped by nature in the high-altitude plains of Bolivia.
Fracturing by the roots. Fracturing by roots, also known as root wedging or root pry, is a geological and physical weathering process caused by the growth of plant roots in joints and fractures of rocks. Here are the key points about this process. 1. Mechanism: as plant roots grow, they seek out available spaces, including existing cracks, joints, or fractures in rocks. As the roots expand, they exert pressure on the surrounding rock, causing it to fracture or widen. 2. Types of rocks affected: root fracturing is most effective in rocks that have existing joints or fractures. The process is commonly observed in sedimentary rocks, especially those with layered structures, where roots can penetrate and exploit existing weaknesses. 3. Contributing factors: the effectiveness of root wedging depends on factors such as the type of plant, the size and strength of the roots, and the characteristics of the rock. In areas with vegetation, the roots of trees and plants play a significant role in this weathering process. 4. Expansion force. The growth of roots creates an expansion force as they push against the surrounding rock. Over time, this force can lead to the widening and propagation of fractures, eventually causing pieces of rock to break off. 5. Effects on weathering. Root fracturing is a form of physical weathering, breaking down rocks into smaller particles. This process contributes to soil formation and the breakdown of rock material into sediments. 6. Landform evolution. Over long periods, root fracturing can contribute to the formation and evolution of certain landforms. For example, in rocky terrains, the combined effects of root growth and weathering can lead to the development of talus slopes or rocky debris. 7. Environmental significance. Root fracturing is part of the broader interaction between vegetation and geology. It plays a role in soil development, nutrient cycling, and the overall shaping of landscapes. Understanding the processes of root wedging is essential in fields such as geology, geomorphology, and soil science, as it contributes to our knowledge of landscape evolution and the interconnected processes of biological and geological systems. Chemical weathering is a geological process that involves the alteration or decomposition of rocks and minerals through chemical reactions. Unlike physical weathering, which involves the mechanical breakdown of rocks, chemical weathering changes the chemical composition of minerals, leading to the formation of new minerals and alteration of rock structures. Here are key points about chemical weathering. 1. Chemical reactions. Chemical weathering occurs through various chemical reactions between minerals and rocks and external agents like water, air, and acids. These reactions transform the original minerals into different substances. 2. Water as a universal agent. Water is a crucial agent in chemical weathering. It can dissolve minerals or facilitate chemical reactions by acting as a medium for ions to move. Rainwater, groundwater, and surface water play significant roles in these processes. 3. Oxidation. Oxidation is a common chemical weathering process where minerals containing iron are exposed to oxygen. This reaction results in the formation of iron oxide, commonly known as rust. The reddish color often observed in weathered rocks is indicative of oxidation. 4. Hydration. Hydration involves the absorption of water molecules into mineral structures, leading to the expansion and alteration of minerals. This process is particularly important in the weathering of certain minerals like feldspar. 5. Carbonation. Carbonation occurs when carbon dioxide, CO2, dissolves in water, forming carbonic acid. This weak acid can react with minerals like limestone and marble, leading to their dissolution and the formation of features such as caves and sinkholes. 6. Hydrolysis. Hydrolysis involves the reaction of minerals with water, resulting in the breakdown of minerals into new substances. For example, feldspar can undergo hydrolysis to form clay minerals. 7. Biological influence. The activity of organisms, such as plants and bacteria, can enhance chemical weathering. Organic acids produced by plant roots, for instance, can contribute to the breakdown of minerals. 8. Effects on landscape. Chemical weathering contributes to the formation of soil and the shaping of landscapes. It is a key process in the development of landforms such as valleys, caves, and karst topography. 9. Temperature influence. Chemical weathering is often more rapid in warmer climates where chemical reactions tend to occur more quickly. Temperature variations can influence the rates of chemical reactions. 10. Time frame. Chemical weathering is generally a slow process that occurs over long geological time scales. The extent of weathering depends on factors like mineral susceptibility, climate, and the presence of certain chemicals. Understanding chemical weathering is crucial for scientists studying geological processes, soil formation, and landscape evolution. It is a fundamental aspect of Earth's dynamic systems. Chemical weathering can be influenced by climatic conditions, and certain climates are associated with higher rates of chemical weathering. Here are some climate-related factors that contribute to higher chemical weathering. 1. Warm and humid climates. Chemical weathering tends to be more pronounced in warm and humid climates. The presence of moisture and higher temperatures accelerates chemical reactions. In these climates, rainfall is often more acidic due to the dissolution of carbon dioxide, which further enhances weathering. 2. Tropical rainforests. Tropical rainforests experience high temperatures and abundant rainfall throughout the year. These conditions contribute to intense chemical weathering. The warm temperatures speed up chemical reactions, and the frequent rainfall provides ample moisture for weathering processes. 3. Subtropical climates, subtropical regions, characterized by warm temperatures and high humidity, also favor chemical weathering. While not as extreme as tropical rainforests, subtropical climates still provide conducive conditions for the breakdown of minerals through chemical processes. 4. Equatorial regions, areas near the equator often experience high temperatures and consistent moisture, promoting both physical and chemical weathering. The combination of warmth and humidity accelerates the decomposition of rocks. 5. Coastal environments. Coastal areas are influenced by a combination of warm temperatures, high humidity, and the presence of salt in the air. Salt water can contribute to chemical weathering, especially in coastal rocks and cliffs. 6. Arid and semi-arid regions. While arid and semi-arid climates are generally associated with physical weathering, for example, mechanical breakdown due to temperature fluctuations, some chemical weathering processes can also occur. Rainfall, though infrequent, can introduce moisture for chemical reactions. 7. High elevation areas. Certain high elevation regions may experience increased chemical weathering due to factors such as increased precipitation at higher altitudes. The presence of acidic precipitation in mountainous areas can contribute to the breakdown of minerals. It's important to note that while climate plays a significant role in chemical weathering, other factors such as the type of rock, mineral composition, and vegetation cover also influence the rates of weathering. Additionally, human activities, such as pollution, can impact the chemistry of rainfall and contribute to accelerated chemical weathering in certain regions. Chemical weathering can affect various types of rocks, but some rocks are more susceptible to chemical weathering due to their mineral composition. Here are some types of rocks that are particularly susceptible to chemical weathering. 1. Limestone. Limestone is composed mainly of the mineral calcite, which is highly soluble in acidic water. Acid rain or slightly acidic groundwater can dissolve calcite, leading to the dissolution and weathering of limestone. 2. Marble. Marble is a metamorphic rock primarily made up of calcite, similar to limestone. It is susceptible to dissolution in acidic conditions, leading to the weathering of the rock. 3. Shale. Shale is a sedimentary rock rich in clay minerals. The minerals in shale can be altered by chemical reactions, and the rock may break down into smaller particles over time. 4. Sandstone. Sandstone is another sedimentary rock that can undergo chemical weathering. The cementing minerals holding the sand grains together may be susceptible to dissolution, weakening the rock. 5. Granite. Granite is an igneous rock composed of minerals such as feldspar, quartz, and mica. The feldspar minerals in granite can be altered by chemical weathering, leading to the decomposition of the rock. 6. Basalt. Basalt is an igneous rock containing minerals like feldspar and pyroxene. Weathering can alter the minerals in basalt, especially in the presence of water and oxygen. 7. Gneiss. Gneiss is a metamorphic rock that may contain minerals like feldspar, quartz, and mica. The susceptibility to chemical weathering depends on the specific mineral composition of the gneiss. It's important to note that the mineral content of rocks is a key factor in determining their response to chemical weathering. Minerals such as feldspar and calcite are more susceptible to dissolution, while quartz is relatively resistant. Additionally, the climate and environmental conditions in a particular region play a significant role in the extent of chemical weathering experienced by rocks. Organic weathering is a type of weathering process that results from the actions of living organisms, particularly plants and microorganisms. This process contributes to the breakdown and alteration of rocks and minerals through various biological activities. Here are some key aspects of organic weathering. 1. Root wedging. Plant roots can exert significant pressure on rocks as they grow and expand. This process, known as root wedging, occurs when plant roots penetrate fractures and crevices in rocks. As the roots expand, they exert force on the surrounding rock, causing it to break apart. 2. Lichen and moss activity. Lichens are symbiotic organisms composed of fungi and algae or cyanobacteria. They can colonize rock surfaces and release organic acids as byproducts of metabolic processes. These acids contribute to the chemical weathering of minerals in the rock. Mosses, too, can absorb and retain water, promoting physical weathering as the water freezes and expands. 3. Microbial weathering. Microorganisms, including bacteria and fungi, play a role in breaking down rocks. Some microorganisms produce organic acids that can dissolve minerals, leading to chemical weathering. Microbial activity is particularly effective in humid and warm environments. 4. Burrowing organisms. Animals such as earthworms and burrowing insects can contribute to organic weathering. Their activities involve the physical breakdown of soil and rocks as they create burrows and passages. This process, known as bioturbation, enhances the exposure of rocks to weathering agents. 5. Decomposition of organic matter. The decay of organic matter, such as dead plants and leaves, contributes to the release of organic acids into the soil. These acids can react with minerals and rocks, initiating chemical weathering processes. Organic weathering is prevalent in terrestrial environments where living organisms interact with rocks and minerals. The combination of physical and chemical processes driven by living organisms can lead to the disintegration and alteration of rocks over time. Plants, particularly certain types like some types of mosses and lichens, can secrete acids that contribute to the weathering and dissolution of minerals in rocks. This process is part of what's known as chemical weathering, where the minerals in rocks react with chemicals produced by living organisms. Additionally, the activities of creatures living in the soil, ranging from microorganisms to larger animals, can have a significant impact on the weathering of rocks. Earthworms, for example, are known to burrow through soil, creating channels that facilitate the movement of water and air. Their activities also contribute to the breakdown of organic matter, releasing acids that can further enhance the chemical weathering of minerals. So, both plants and soil-dwelling organisms play essential roles in the complex processes of rock weathering, contributing to the transformation of geological features over time. Soil formation, also known as pedogenesis, is influenced by a variety of factors that interact in complex ways. Here are the key factors determining soil formation. 1. Parent material, lithology. 2. Climate. 3. Organisms. 4. Topography, relief. 5. Time. 6. Human activity. 7. Parent material composition. 8. Biological activity. 9. Water. Soil formation, also known as pedogenesis, is influenced by a variety of factors that interact in complex ways. Here are the key factors determining soil formation. 1. Parent material, lithology. The type of rock or sediment from which the soil is derived greatly influences soil properties. Different rocks weather and break down into soil particles at varying rates. 2. Climate. Climate is a major factor in soil formation. Temperature and precipitation influence the rate of weathering, the types of vegetation, and the accumulation of organic matter. The combination of these factors determines the soil's profile and characteristics. 3. Organisms. Living organisms, including plants, animals, fungi, and microorganisms, contribute to soil formation. Plant roots release organic acids that weather minerals, and microbial activity breaks down organic matter, releasing nutrients. 4. Topography, relief. The landscape, including slope, aspect, and elevation, affects soil development. Sloped areas may have differences in soil depth and erosion, while aspects, direction the slope faces, influence temperature and moisture conditions. 5. Time. Soil formation is a slow process that occurs over geological time. The age of a soil influences its characteristics, with older soils generally having more developed horizons. 6. Human activity. Human activities such as agriculture, deforestation, and urbanization can significantly impact soil formation. Land use changes can alter vegetation cover, disturb the soil, and lead to erosion. 7. Parent material composition. The mineral composition and chemical characteristics of the parent material influence the type of minerals present in the soil and affect nutrient availability. 8. Biological activity. The decomposition of organic matter by microbes, fungi, and other soil organisms contributes to the formation of organic-rich soil horizons. 9. Water. The availability and movement of water in the soil affect weathering processes, nutrient transport, and the development of soil structure. Understanding these factors and their interactions is crucial for soil scientists and land managers to assess soil quality, predict land use impacts, and implement sustainable land management practices. Climate has a profound impact on soil formation, influencing various processes that shape the characteristics of soils. Here are the key effects of climate on soil formation. 1. Weathering rates. Climate influences the rate of weathering, which is the breakdown of rocks into soil particles. In regions with high temperatures and abundant moisture, chemical weathering is accelerated, leading to faster soil formation. 2. Temperature. Temperature affects the intensity of physical and chemical weathering. In warmer climates, chemical reactions are often more rapid, leading to faster breakdown of minerals and rocks. Temperature also influences microbial activity in the soil. 3. Precipitation. The amount and distribution of precipitation impacts soil development. Excessive rainfall can cause leaching, where minerals are washed away, affecting the soil's nutrient content. Conversely, arid climates may lead to the accumulation of certain minerals. 4. Freeze-thaw cycles. In cold climates, freeze-thaw cycles can contribute to physical weathering. Water enters cracks in rocks, freezes, expands, and causes the rock to break apart. This process helps create smaller particles for soil formation. 5. Vegetation type. Climate determines the types of plants that can thrive in an area. The presence and characteristics of vegetation influence the input of organic matter into the soil, affecting soil structure and nutrient cycling. 6. Erosion. Climate influences erosion rates, which can transport soil particles and affect the development of soil horizons. Wind and water erosion are more prevalent in certain climatic conditions. 7. Humidity. Humidity levels affect soil moisture content. High humidity can lead to the retention of moisture in soils, influencing microbial activity, nutrient cycling, and the decomposition of organic matter. 8. Evaporation rates. In arid climates, high evaporation rates can lead to the accumulation of salts in the soil. This process, known as salinization, can impact soil fertility and structure. 9. Seasonal changes. Climate variations between seasons contribute to the formation of soil horizons. For example, the freezing and thawing of soil during winter can lead to the development of distinctive soil characteristics. 10. Microbial activity. Climate conditions, especially temperature and moisture, influence the activity of soil microorganisms. Microbial processes, such as decomposition, nutrient cycling, and organic matter transformation, play a crucial role in soil formation. Understanding the regional climate is essential for predicting soil characteristics, fertility, and suitability for various land uses. Soil scientists use climate data along with other factors to classify soils and provide recommendations for sustainable land management practices. Absolutely, you've highlighted a fundamental principle in soil science. Climate is often considered the primary factor in soil formation, and it influences several key processes that shape the characteristics of soils. Here's a brief overview of how climate interacts with these processes. 1. Weathering. Climate, especially temperature and precipitation patterns, plays a crucial role in the rate and type of weathering. In warmer and wetter climates, chemical weathering tends to be more pronounced, breaking down rocks into soil particles. 2. Vegetation. The types of plants that can grow in an area are largely determined by climate. Different vegetation types contribute varying amounts of organic matter to the soil through processes like leaf litter decomposition, affecting soil structure and nutrient content. 3. Soil washing. Erosion and leaching. Precipitation and temperature influence erosion rates. High rainfall can lead to soil erosion, transporting soil particles downslope. Excessive precipitation can also cause leaching, where minerals are washed away from the soil. 4. Organism activities. Climate affects the types of organisms that inhabit the soil. Microorganisms, insects, and other soil fauna play crucial roles in nutrient cycling, organic matter decomposition, and soil structure development. Their activities are influenced by temperature and moisture conditions. Understanding the interplay between these factors under different climatic conditions helps soil scientists classify soils and predict their characteristics. This information is valuable for agriculture, land management, and environmental studies. The climate in a region has a profound impact on the dominant weathering processes and, consequently, on soil formation. Let's delve a bit deeper into how climate influences these processes. 1. Hot and humid regions. Chemical dissolution. The combination of high temperatures and abundant moisture accelerates chemical weathering. Water acts as a solvent, facilitating the breakdown of minerals in rocks. This leads to the formation of clay minerals and the leaching of nutrients, influencing soil composition. Fast decomposition. Organic matter, such as plant debris, decomposes rapidly in warm and humid conditions. This contributes to the development of fertile soils rich in organic material. 2. Cold and arid regions. Physical dissolution. In colder climates, freeze-thaw cycles can cause physical breakdown of rocks. Water enters cracks in rocks, freezes, expands, and can eventually fragment the rock. This process is known as frost action or freeze-thaw weathering. Slower weathering. The lower temperatures and reduced water availability slow down chemical weathering processes. As a result, soil development tends to be slower in cold and arid regions, and soils may have a higher proportion of unweathered rock fragments. Understanding these climate-induced processes is essential for predicting the characteristics of soils in different regions, which, in turn, informs land use planning, agriculture, and environmental management. In regions with high rainfall and moisture, a process known as leaching becomes significant. Let's delve into this process. 1. Leaching in moist areas. High rainfall. Moist areas often experience high levels of rainfall, which can lead to an increased movement of water through the soil profile. Nutrient transport. As water percolates through the soil, it can dissolve and carry away soluble nutrients from the upper soil layers to the lower layers. This process is known as leaching. Nutrient depletion. Continuous leaching can result in the depletion of nutrients, particularly the more soluble ones like nitrates and potassium, from the topsoil. Soil nutrient stratification. Over time, this leaching can lead to a stratification of soil nutrients, with nutrient-rich layers forming deeper in the soil profile. 2. Consequences for soil fertility. Nutrient-poor topsoil. The upper layers of the soil may become relatively nutrient-poor due to leaching, impacting the fertility of the soil for plant growth. Subsoil accumulation. Nutrients that leach down may accumulate in the subsoil, creating a nutrient reservoir deeper in the soil profile. Understanding the leaching process is crucial for managing soil fertility, especially in agriculture. Techniques such as nutrient management, cover cropping, and agroforestry are often employed to mitigate nutrient loss through leaching and enhance overall soil health. In arid regions, where there is limited rainfall and moisture, the process of leaching is significantly reduced. This has important implications for soil composition, leading to the accumulation of certain substances. Let's delve into this. 1. Low leaching in arid regions. Limited rainfall. Arid regions experience low and irregular rainfall, resulting in less water moving through the soil profile. Reduced leaching. With limited water percolation, there is a reduced capacity for leaching, the process by which soluble substances are washed down through the soil. 2. Accumulation of lime and salts. High evaporation. In arid climates, water from rainfall or irrigation may evaporate more quickly than it infiltrates the soil. Salt and lime concentration. As water evaporates from the soil surface, it leaves behind salts and minerals. Over time, this process can lead to an accumulation of salts, including common ones like sodium chloride, table salt, and lime, calcium carbonate. Soil salinization. The buildup of salts in the soil, known as soil salinization, can affect soil structure and fertility. Excessive salts can be detrimental to plant growth. 3. Challenges for agriculture. Saline soils. Soils with high salt concentrations can be less suitable for agriculture as many plants are sensitive to high salt levels. Alkaline soils. Accumulation of lime can lead to alkaline soils, which may also impact plant nutrient availability. Understanding these soil characteristics is crucial for agricultural practices in arid regions. It often involves strategies like proper irrigation management, soil amendments, and selecting crops that are adapted to saline conditions. The presence and accumulation of organic matter in soil are indeed influenced by climatic factors. Let's explore this further. 1. Organic matter accumulation. Climate influence. The rate of organic matter decomposition and accumulation is closely tied to climate conditions. Biological activity. In regions with a temperate climate and ample moisture, biological activity, including the breakdown of plant residues by microorganisms, is more rapid. Humid regions. Areas with higher rainfall and moderate temperatures often support lush vegetation. The decomposition of plant material is accelerated in these conditions, leading to the accumulation of organic matter in the soil. Organic horizon. Over time, this accumulated organic material contributes to the formation of distinct soil horizons, such as the O horizon, organic horizon, rich in decomposed plant matter. 2. Effects on soil properties. Nutrient content. Organic matter is a key source of nutrients for plants. In regions where organic matter accumulates, the soil tends to be richer in nutrients. Soil structure. Organic matter plays a vital role in improving soil structure. It enhances water retention, aeration, and nutrient availability. 3. Challenges in arid climates. Limited organic accumulation. In arid and semi-arid regions, the limited availability of moisture hinders the rapid breakdown of plant residues. As a result, the accumulation of organic matter in these soils is generally lower. Slow decomposition. Dry conditions slow down microbial activity, reducing the decomposition rate of organic materials. Understanding the relationship between climate and organic matter content is crucial for sustainable agriculture and soil management. Practices such as cover cropping, mulching, and organic amendments are often employed to enhance organic matter levels in soils, particularly in regions where natural accumulation is slower. The strength and type of vegetation in an area have a direct impact on the organic content of the soil. Let's delve deeper into this correlation. 1. Vegetation strength and soil organic matter. Arid climates. In arid and semi-arid climates, where water availability is limited, vegetation tends to be sparse and adapted to conserve water. The scarcity of plant material and slower decomposition result in lower organic matter content in the soil. Lush vegetation. Conversely, regions with abundant rainfall and more favorable climatic conditions support lush vegetation. The continuous growth and shedding of plant material contribute to higher organic matter accumulation in the soil. 2. Organic matter's role in soil fertility. Nutrient cycling. Organic matter serves as a reservoir for essential nutrients. In areas with rich organic content, there's a higher capacity for nutrient cycling, benefiting plant growth. Microbial activity. The presence of organic matter supports microbial activity. Microorganisms play a crucial role in decomposing organic residues, releasing nutrients in forms accessible to plants. 3. Soil health and productivity. Soil structure. Organic matter improves soil structure by enhancing aggregation. This, in turn, promotes better water retention, drainage, and root penetration. Moisture retention. Soils with adequate organic matter can better retain moisture, an important factor in sustaining vegetation. 4. Management considerations. Soil amendments. In agricultural practices, incorporating organic amendments, compost, cover crops, etc., is a common strategy to enhance organic matter content, particularly in arid or degraded soils. Conservation practices. Implementing conservation practices, such as cover cropping and reduced tillage, helps preserve and build organic matter in soils. Understanding the interplay between vegetation, climate, and soil organic matter is crucial for sustainable land management and agricultural productivity. It guides practices aimed at improving soil health and fertility. Soil dynamics, especially in areas with high rainfall, has significant features. 1. Erosion and organic matter loss. High rainfall. Regions with abundant rainfall may experience higher rates of soil erosion. Intense rain can lead to surface runoff, carrying away topsoil along with organic matter, humus. This process, known as erosion, can result in the loss of valuable soil components. 2. Vegetation and soil organic matter. Abundant vegetation. While high rainfall supports lush vegetation, the relationship between vegetation and soil organic matter can be complex. In some cases, the abundant growth of vegetation contributes organic material to the soil through leaf litter, root turnover, and decaying plant matter. 3. Organic matter redistribution. Transport by water. On the other hand, as you rightly pointed out, water can also transport organic matter away from certain areas. This redistribution can lead to variations in organic matter content across the landscape. 4. Mitigating erosion and enhancing soil health. Conservation measures. Implementing conservation practices becomes crucial in areas prone to erosion. Techniques such as contour plowing, cover cropping, and afforestation can help reduce soil erosion and enhance organic matter retention. 5. Land use and management. Agricultural practices. Sustainable agricultural practices, including agroforestry and agroecological approaches, aim to minimize soil disturbance and maintain or increase organic matter levels. 6. Soil testing and monitoring. Site-specific approaches, conducting soil tests and regular monitoring help tailor management strategies to the specific needs of an area. This includes adjusting practices to counteract organic matter loss. The relationship between rainfall, vegetation, and soil organic matter involves a delicate balance influenced by factors such as erosion, deposition, and land management practices. Sustainable land use and conservation measures are essential for maintaining soil health and fertility, especially in regions with dynamic environmental conditions. The color of organic soils, often referred to as peat or organic-rich soils, is influenced by the presence of organic matter, particularly decomposed plant material. Here's a bit more detail. 1. Coloration by organic matter. Brown or black, the organic matter in these soils contains carbon compounds. When this organic matter decomposes, it releases humic substances, which can impart a brown to black color to the soil. 2. Humic substances. Humus formation. Humic substances are a key component of humus, which is the organic component of soil formed by the decomposition of plant and animal matter. These substances are dark colored, and their concentration contributes to the soil's overall color. 3. Decomposition stages. Peat formation. In the early stages of decomposition, organic soils may contain a significant amount of peat. Peat is partially decomposed organic matter, and it can give the soil a brownish color. As decomposition progresses, the soil may become darker and more similar to typical mineral soils. 4. Indicators of organic soils. Visual inspection. The coloration is often one of the visual indicators used to identify organic soils. Besides color, organic soils may have distinct characteristics such as a spongy texture, high moisture retention, and a distinctive smell associated with decomposing organic matter. 5. Environmental significance. Carbon storage. Organic soils are significant for their role in storing carbon. They act as carbon sinks, and changes in land use or drainage can impact the release of stored carbon into the atmosphere. 6. Land use considerations. Agricultural use. While organic soils can be fertile, their use in agriculture often requires careful management. Drainage is a common practice to make these soils suitable for cultivation, but it needs to be done cautiously to avoid excessive decomposition and subsidence. Understanding the color variations in soils provides valuable information about their composition, organic content, and potential uses. It's an essential aspect of soil classification and management. The type of bedrock or parent material has a significant influence on soil formation. Here's how. 1. Mineral composition. Rock minerals. The minerals present in the bedrock determine the initial mineral composition of the soil. For example, limestone bedrock will contribute calcium carbonate to the soil, affecting its pH and nutrient content. 2. Weathering processes. Physical and chemical weathering. Over time, the bedrock undergoes physical and chemical weathering processes. Physical weathering involves the breakdown of rock into smaller particles without changing its chemical composition. Chemical weathering alters the mineral composition of the rock, producing new minerals and releasing ions into the soil. 3. Soil texture. Particle size. The breakdown of bedrock influences the particle size distribution in the soil. Weathering can lead to the formation of clay, silt, and sand particles. The combination of these particles determines the soil texture. 4. Nutrient content. Mineral elements. The minerals present in the bedrock contribute essential nutrients to the soil. For example, granite contains minerals like feldspar, which releases potassium as it weathers. This influences the availability of nutrients in the soil. 5. Soil pH. Limestone influence. Soils developed on limestone bedrock tend to be alkaline due to the presence of calcium carbonate. Conversely, soils from granite bedrock are often more acidic. 6. Parent material characteristics. Influence on soil properties. The chemical, physical, and mineralogical properties of the parent material are inherited by the soil. The initial characteristics of the parent material shape the early stages of soil development. 7. Soil profile development. Horizon formation. As weathering continues, distinct soil horizons, layers, may develop. The characteristics of these horizons are influenced by the nature of the bedrock. Understanding the type of bedrock in a region provides insights into the potential soil properties, fertility, and challenges for various land uses. Different bedrock types contribute unique qualities to soil, making them suitable or unsuitable for specific purposes. The resistance of rocks to weathering is influenced by their hardness and mineral composition. Here's a bit more detail. 1. Hard rocks. Resistance to weathering. Hard rocks, often composed of minerals like quartz and feldspar, are resistant to weathering processes. Erosion resistance. Their durability makes them less prone to erosion and breakdown, maintaining their original structure over time. Formation of residual soils. Weathering of hard rocks can result in the formation of residual soils that retain some of the characteristics of the parent rock. 2. Soft rocks. Susceptibility to weathering. Soft rocks, composed of minerals like clay and gypsum, are more susceptible to weathering. Erosion proneness. they can be easily eroded and broken down into finer particles due to the influence of physical and chemical weathering agents. Formation of sedimentary soils. Soft rocks contribute to the formation of sedimentary soils as their particles can be transported and deposited by water, wind, or ice. 3. Weathering agents. Chemical weathering. Soft rocks are often more susceptible to chemical weathering, where minerals are altered through processes like hydration and dissolution. Physical weathering. Hard rocks are more resistant to physical weathering, which involves processes like freeze-thaw cycles and abrasion. 4. Landscape features. Topography. The type of rock in an area contributes to the landscape features. Hard rocks may lead to the formation of rugged landscapes, while soft rocks may contribute to the development of softer, more easily eroded features. Understanding the hardness and mineral composition of rocks is crucial for assessing their resilience to weathering, shaping the landscape, and influencing soil formation processes. The composition of rocks significantly influences the rate of weathering and, consequently, soil formation. Granite and tuff represent two contrasting rock types in terms of their weathering characteristics. 1. Granite. Hardness and resistance. Granite is a hard and resistant igneous rock composed mainly of quartz, feldspar, and mica. Slow weathering. Due to its hardness and mineral composition, granite weathers slowly. The minerals in granite are more resistant to chemical breakdown. Long soil formation. As granite dissolves and weathers at a slower rate, the process of soil formation from granite is generally longer. 2. Tuff. Soft and porous. Tuff is a volcanic rock composed of volcanic ash and other volcanic debris. It is generally softer and more porous than granite. Rapid weathering. Tuff weathers more easily due to its softer nature. Both physical and chemical weathering can act more efficiently on tuff. Short soil formation. The weathering of tuff leads to a quicker process of soil formation compared to granite. This illustrates how the mineral composition, hardness, and porosity of rocks play crucial roles in shaping landscapes and determining the timeline for soil development. It's a fundamental principle in understanding the Earth's processes and the formation of different soil types. The type and composition of bedrock are fundamental factors influencing the characteristics of the resulting soil. Here's a breakdown of how different types of bedrock contribute to various soil types. 1. Calcareous soil. Bedrock type: limestone and other calcium-rich rocks. Characteristics: high in calcium carbonate, lime. Often alkaline in nature. Use: suitable for crops that thrive in alkaline conditions. 2. Phosphorus soil. Bedrock type: rocks rich in phosphorus minerals. Characteristics: contains higher levels of phosphorus, an essential nutrient for plant growth. Use: beneficial for plants requiring phosphorus, such as those flowering and fruiting. 3. Clayey soil. Bedrock type: rocks rich in clay minerals, for example, shale. Characteristics: fine particles, good water retention, can be heavy and compact. Use: holds nutrients well but may require amendments for better drainage. 4. Sandy soil. Bedrock type: sandstone and rocks with a high proportion of sand. Characteristics: coarse particles, well draining, may not retain nutrients as effectively. Use: suitable for plants that thrive in well draining conditions. 5. Silty soil. Bedrock type: rocks with a mix of silt-sized particles. Characteristics: intermediate particle size, good fertility, retains water better than sand. Use: versatile soil type, suitable for various crops. Understanding the geological origin of the bedrock provides valuable insights into the potential characteristics of the resulting soil. Farmers and land managers often take these factors into consideration when planning agricultural activities or assessing soil quality. The factor of time is a crucial aspect of soil formation. Soil development is a gradual process influenced by various factors, and the duration of these processes contributes to the final characteristics of the soil. Here's a breakdown of the effect of time in soil formation. 1. Initial weathering. Early stage, physical and chemical weathering processes begin breaking down parent material. Effect: initial soil particles form, but soil horizons, layers, are not well defined. 2. Horizon development. Intermediate stage, continued weathering leads to the formation of distinct soil horizons. Effect: horizons such as topsoil, a horizon, subsoil, B horizon, and, in some cases, the accumulation of organic matter, O horizon, become more defined. 3. Accumulation of organic matter. Over time, the gradual accumulation of organic material from plant and animal remains. Effect: a well-developed horizon contributes to soil fertility and structure. 4. Mineral accumulation. Long-term, leaching and mineral accumulation continue over extended periods. Effect: development of specific soil characteristics based on mineral content and nutrient availability. 5. Soil profile maturation. Extended time, soil profile becomes more mature and stable. Effect: the soil's physical, chemical, and biological properties reach a relatively stable state, influencing its overall fertility and suitability for various uses. 6. Pedogenesis, soil formation. Continuous process, soil formation is an ongoing process influenced by environmental factors. Effect: soil properties may continue to evolve, but at a slower rate compared to earlier stages. Understanding the temporal aspect of soil formation helps in predicting soil characteristics, fertility, and suitability for specific land uses. It also emphasizes the importance of long-term management strategies for sustainable agriculture and environmental conservation. The weathering of bedrock is a complex process that involves the gradual breakdown of rocks into smaller particles over an extended period. The following steps illustrate the stages of bedrock weathering and the time required for horizon development in the soil. 1. Initial weathering. Time frame: hundreds to thousands of years. Process: physical and chemical weathering processes begin as rocks are exposed to environmental factors such as temperature fluctuations, moisture, and biological activity. 2. Organic matter settlement. Time frame: over time, as vegetation establishes and organisms contribute to soil formation. Process: degradation: products from plants and other organisms settle on the weathered rock surfaces, initiating the accumulation of organic matter. 3. Disintegration of organic matter. Time frame: ongoing process spanning hundreds to thousands of years. Process: the organic matter undergoes decomposition, contributing to the formation of the soil organic horizon, horizon, and providing essential nutrients for soil development. 4. Horizonization of the soil. Time frame: extended periods of soil development. Process: the ongoing interplay of weathering, organic matter decomposition, and mineral accumulation leads to the formation of distinct soil horizons, A, B, and sometimes C horizons. This process requires hundreds or thousands of years to result in a well-developed soil profile. 5. Soil maturity. Time frame: thousands of years. Process: the soil profile continues to mature, with horizons becoming more defined, and the soil stabilizes into a relatively consistent state influenced by climatic, geological, and biological factors. Understanding the gradual nature of bedrock weathering and soil formation emphasizes the importance of sustainable land management practices. It also highlights the long-term commitment required for soil improvement and conservation efforts. Landforms play a crucial role in the process of soil formation, influencing factors such as drainage, erosion, and the accumulation of materials. Here's a breakdown of the effects of landforms on soil formation. 1. Erosion and deposition. Landform types: slopes, valleys, plains, and hills. Effect: slopes may experience erosion due to gravity, leading to the removal of topsoil. Valleys often accumulate sediments deposited by water. Plains may have well-developed soils due to sedimentation, while hills can be characterized by the movement of soil downslope. 2. Drainage patterns. Landform types: valleys, plains, and slopes. Effect: the shape of the land determines water drainage patterns. Well-drained soils in upland areas may support specific vegetation, while poorly drained soils in valleys may have different characteristics. Drainage affects soil aeration, nutrient availability, and microbial activity. 3. Parent material accumulation. Landform types: floodplains, alluvial fans, and terraces. Effect: these landforms often accumulate materials transported by water or wind, influencing the parent material of the soil. Floodplains, for example, may have fertile soils due to the deposition of nutrient-rich sediments. 4. Slope aspect. Landform types: hills and slopes. Effect: the aspect of a slope, whether it faces north, south, east, or west, influences sunlight exposure and temperature. This, in turn, affects vegetation growth and decomposition rates, influencing soil organic matter content. 5. Weathering rates. Landform types, mountains, plateaus, and plains. Effect: the exposure of landforms to weathering agents like wind, water, and temperature determines the rate of rock breakdown. Mountains with exposed rock surfaces may experience faster weathering compared to protected plains. 6. Vegetation zones. Landform types, valleys, slopes, and plateaus. Effect: different landforms may support specific vegetation zones based on factors like elevation, soil type, and moisture. Vegetation contributes to organic matter and influences nutrient cycling. 7. Soil texture and composition. Landform types, riverbanks, coastal areas, and hills. Effect: the proximity to water bodies, elevation changes, and geological features influence soil texture and composition. Coastal areas may have sandy soils, riverbanks may have alluvial soils, and hills may have loamy soils. Understanding the impact of landforms on soil formation is essential for sustainable land use planning, agriculture, and conservation efforts. It highlights the dynamic interactions between geological, climatic, and biological factors that shape the characteristics of soils in different landscapes. Elevation, aspect, and slope angle are critical factors in soil formation, influencing various soil properties and characteristics. Here's an overview of their effects. 1. Elevation. Effect on temperature and climate. As elevation increases, temperatures generally decrease. This impacts climate, affecting factors such as precipitation, evaporation, and snowmelt. These climatic variations influence the rate of weathering, vegetation types, and organic matter decomposition. Vegetation zones. Different elevations support distinct vegetation zones, influencing the types of organic matter and nutrients present in the soil. For example, mountainous regions may have alpine vegetation at higher elevations and forests at lower elevations. 2. Aspect, slope orientation. Solar exposure. Aspect refers to the compass direction a slope faces, north, south, east, or west. The orientation influences solar exposure, with south-facing slopes receiving more sunlight in the northern hemisphere. This affects temperature, moisture, and vegetation. Microclimate. Different aspects can create microclimates. For instance, north-facing slopes may be cooler and moister, influencing the types of plants and organisms present. South-facing slopes may be warmer and drier. 3. Slope angle. Erosion and soil movement. Steeper slopes are more prone to erosion, leading to the removal of topsoil. The angle of the slope affects water runoff, which influences drainage patterns and sediment transport. It can result in the formation of terraces and other landforms. Soil depth. Steeper slopes may have shallower soils due to erosion, while gentle slopes may accumulate more soil over time. This influences the depth of the soil profile and its capacity to retain water and nutrients. 4. Soil composition. Erosion and sedimentation. Elevation plays a crucial role in shaping local climates, which, in turn, influence various environmental processes. Here's a more detailed breakdown. 1. Temperature. As elevation increases, temperatures generally decrease. This is known as the lapse rate, where the air temperature drops with altitude. Cooler temperatures at higher elevations impact the rate of physical and chemical weathering processes. 2. Precipitation. Elevation can affect precipitation patterns. Mountain ranges often experience orographic precipitation, where moist air is forced to rise, cool, and condense, leading to increased rainfall on windward slopes and rain shadows on the leeward side. 3. Vegetation zones. Different elevations support distinct vegetation zones, often referred to as altitudinal vegetation belts. For example, at lower elevations, you might find deciduous forests. As you ascend, you may encounter coniferous forests. At higher elevations, alpine vegetation or tundra may prevail. 4. Soil formation. Temperature, precipitation, and vegetation significantly influence soil formation. The type of soil at a specific elevation is closely tied to the local climate and the types of plants that can thrive. 5. Hydrological cycle. Elevation affects the hydrological cycle. Higher elevations may be the source of rivers and streams that flow down to lower elevations. The drainage patterns and availability of freshwater resources are intricately linked to elevation. 6. Microclimates. Within a mountainous region, different elevations can create microclimates. North-facing slopes may have cooler and moister conditions, influencing the types of plants and organisms present. South-facing slopes may experience more sunlight and warmth. 7. Glacial processes. At very high elevations, glaciers may form. Glacial processes, including erosion and deposition, shape the landscape and contribute to the formation of characteristic landforms like cirques, aretas, and moraines. Understanding the impact of elevation on climate and environmental processes is essential for various disciplines, including ecology, geology, and agriculture. It contributes to our knowledge of regional variations and helps in making informed decisions regarding land use and conservation. The process you're describing is often referred to as soil development or soil horizonation. It involves the formation of distinct layers or horizons in the soil profile over time. Here's a more detailed explanation. 1. Top of slopes, summit. At the summit or higher parts of slopes, the soil is usually thinner. This is because the initial stages of soil formation involve the breakdown of rock into smaller particles through weathering processes. The finer, weathered material is then transported downslope by various factors such as gravity, water, and wind. 2. Mid-slope areas. As the weathered material accumulates downslope, the soil becomes thicker in mid-slope areas. Here, you may start to see the development of distinct soil horizons. The breakdown of minerals, organic matter accumulation, and other soil-forming processes contribute to this layering. 3. Bottom of slopes, toe slopes. The lower parts of slopes, near the base or toe slopes, often have the thickest soil. This is where accumulated material from higher elevations has settled over time. These areas may have well-developed soil profiles with distinct horizons, including topsoil, a horizon, subsoil, B horizon, and, in some cases, parent material, C horizon. The process of soil horizonation involves the interaction of climate, vegetation, topography, and time. Each soil horizon has unique characteristics, and the overall soil profile reflects the dynamic interplay of these factors over an extended period. This soil development process is crucial for understanding the suitability of soils for various purposes, including agriculture, construction, and ecosystem health. Soil scientists often study these profiles to assess soil quality, fertility, and potential land use. The exposure of slopes to sunlight, known as aspect, significantly influences the microclimate and, consequently, soil formation. Here's how the northern and southern slopes differ. 1. Northern slopes generally receive less direct sunlight. Experience cooler temperatures due to reduced solar radiation. Retain more moisture since they are less prone to evaporation. As a result, soil on northern slopes tends to be cooler and moister. 2. Southern slopes receive more direct sunlight, leading to warmer temperatures. Experience greater evaporation, which can reduce soil moisture. The warmer and drier conditions on southern slopes influence the types of plants that can thrive there. Soils on southern slopes may be warmer and drier compared to northern slopes. These differences in temperature and moisture content play a crucial role in determining the types of vegetation, the rate of weathering, and the overall soil characteristics on each slope. It's a fascinating aspect of soil science and geomorphology, showcasing how the interaction of sunlight and topography influences the local environment. The influence of elevation, aspect, and slope angle on temperature and humidity directly impacts soil formation. The southern slopes of the Taurus Mountains, with their higher temperatures and increased humidity, create conditions conducive to more efficient soil formation compared to the northern slopes. This difference in environmental factors contributes to variations in vegetation, organic matter decomposition rates, and overall soil development. The interplay between climate and topography plays a crucial role in shaping the characteristics of soils in different geographical locations. Vegetation and living organisms play a vital role in soil formation through various processes. Here are some key aspects of their impact. 1. Root action. Plant roots penetrate the soil and contribute to physical weathering by exerting pressure on rocks. As roots grow and decay, they create pore spaces in the soil, enhancing water infiltration. 2. Organic matter decomposition. Dead plant material, such as leaves and stems, falls to the ground and decomposes. Microorganisms break down organic matter, forming humus, which improves soil structure and fertility. 3. Nutrient cycling. Plants absorb nutrients from the soil, and when they die, these nutrients are returned to the soil through decomposition. This cycling of nutrients is crucial for maintaining soil fertility. 4. Microbial activity. Microorganisms, including bacteria and fungi, contribute to the decomposition of organic matter. Some microorganisms form symbiotic relationships with plants, aiding in nutrient uptake. 5. Soil fauna. Earthworms and other soil organisms burrow through the soil, improving aeration and drainage. Their activities also contribute to the breakdown of organic material. 6. Biological weathering. Lichens and mosses can initiate the breakdown of rocks through the release of acids during their growth. 7. Vegetative cover. Plant cover protects the soil from erosion by wind and water. Different types of vegetation influence soil characteristics, such as acidity and nutrient content. 8. Microbial exudates. Microorganisms release substances known as exudates, which can influence soil structure and nutrient availability. In summary, the interactions between plants, microorganisms, and other living organisms contribute to the dynamic processes of soil formation, ensuring the development of a fertile and stable soil profile. The key events in soil formation revolve around the settling of plants on the parent material, the gradual decomposition of the parent material facilitated by acids from plant roots, and the breakdown of plant residues into organic material that integrates with the soil. These processes are essential for the transformation of raw materials into fertile soil. Without these fundamental events, soil formation cannot take place, highlighting the intricate relationship between plants, decomposition, and the organic components crucial for soil development. The organisms inhabiting the soil play a dual role in the process. They contribute significantly to the decomposition of organic matter, aiding in the breakdown of plant residues and other materials. Additionally, these soil-dwelling creatures facilitate the absorption of nutrients by plants, creating a symbiotic relationship that enhances the overall fertility and health of the soil. The intricate web of interactions between plants, decomposers, and other soil organisms underscores the dynamic and interconnected nature of soil ecosystems.